So, what I was talking about that after discussing the acid-base equilibria in detail in chapter 14, the chapter 15 is a brief description of the equilibrium in other types of reactions. And one of the most important in those reactions is precipitation. Okay, so precipitation is actually the dissolution. Precipitation is actually where the solids are going to be formed. Dissolution is opposite to the precipitation when the solids are going to dissolute into respective ions. Okay, the both phenomena are important in chemistry. Either the precipitate or the solid is going to be formed, or solid is going to be disintegrated. You can say that's what we call dissolute in chemistry. It's important. There's many important applications where we want the solid to be dissolute, right? Where there are certain applications in chemistry where we want solids to appear. There's another definition of acid and bases. It's called Lewis acid and base definition. It's important to understand that because there's going to be a different types of acids and bases based on this definition that we're going to come across when we are talking about precipitation and dissolution. And we see that how the multiple equilibriums are going to be achieved in the chemical reactions. Precipitation and dissolution, there's a lot more detail given to you. What are the applications? Okay, this is about controlling the equilibrium between a slightly soluble ionic solid and an aqueous solution of its ions. Okay, we can control equilibrium by having the concern. You already know about the Le principle, so we know we can control things. So medical laboratories, blood samples, these are the examples. Okay, where you might have soluble ionic solids and aqueous solution of its ions. Would you want them it to be more into ion, or you want it to be more into the solid? Okay, and there are different applications. Like say in the blood sample, we want to keep ions into the ionic state. We do not want things to solidify, and like seawater for magnesium, mining of seawater for magnesium, and formulation of over-the-counter medications and milk of magnesia, antacids, etc. Then treating the presence of hot water in the home water. They all go through the applications of either precipitation or dissolution. Okay, precipitation, precipitation or dissolution. If we want a dissolution to be prevented, there are application about that. And 2-decay is actually an example of that, where the ionic compound is calcium hydroxyapatite. Okay, and that dissolves, and we do not want that to dissolve. There, we are preventing the dissolution of the ionic compound. Okay, because that's going to be the 2-decay. Sometimes we want a substance to dissolve. Okay, so calcium carbonate in chewable antacid to dissolve because the carbonate ions produced in this process help soothe an upset stomach. Okay, they're going to take up the protons on themselves. How we can control the dissolution of a slightly soluble ionic solid by the application of Le Chatelier's principle is again kind of a repetition here. How to use equilibrium constant of the reaction, okay, the equilibrium constant of the reaction to determine the concentration of ions present in a saturated. So this is exactly the way we go through the ice charts. Okay, so if the equilibrium constant is given to you, you're going to go through the ice chart to find out the concentration of the ions present in the saturated solution. What does that mean by saturated solution? They say that once the possible dissolution has happened, I mean, 100% of the dissolution that you have achieved, and that 100% is a different capacity of different compounds. Okay, it's different in different compounds. So going back to this here, you have to remember your solubility charts. Okay, you have already memorized that from Gen Chem 11. If not, then it's a good idea that you go by that and try to understand what these rules are. Okay, which type of compounds are going to be soluble, where the compounds are going to be insoluble with certain exceptions in it. So when you go about the solubility and precipitation again, which is kind of a repetition in this chapter, what you have learned so far is some ionic compounds do not dissolve in water, and that's not true because they are actually dissolved to an extent that we consider insignificant, but they are soluble to some extent. So these were called insoluble compounds. Our understanding is that they did not dissociate into ions when placed in water, Compounds that did dissolve by dissociating into their ions, we call them soluble, right? That's how they're going to go ionic compound. When talking about the ionic compound, it's not about the molecular compound, but when we are talking about the ionic compound, we know when we add it into the solution form, we want to see if a ionic compound is soluble in water or not. Then we're going to be adding it into the solution, into the water, into the solvent, and then we assume, not assume, we are sure that they're going to dissociate. They're going to dissolute into respective ions, and that's the phenomena of solubility. Why they? Because plus going to go with the negative end of the water, and the negative is going to go with the plus end of it. We have discussed that plenty of times, so that's not the case here. An equilibrium exists between the precipitate and its ion. That's when it is going on, and definitely they're going to go into an equilibrium state as well. When solid dissociates, there's going to be an equilibrium thing, okay? Because if more and more concentration increase here, then it will start going back into the solid form. So that's why we want to control that where we can get the maximum of the ions and minimum of the solid, where we can have maximum of the solid, we can have minimum of the ions. So that's where we can play. In reality, what I have already said is even insoluble compound dissolve to some extent. Okay, it's very small, but it is. These are called sparingly soluble. That we earlier we were considering them as insoluble. Now insolubles are sparingly soluble salts. Okay, so an equilibrium exists between the precipitate and its ion. Okay, so that's what I was trying to say. Even if I try to show you CH3COO, but that's not a solid. But that's where we were talking about an acid. It's an aqueous situation. Here we are talking about the solids equilibrium in the dissolution of the solid. So equilibrium exists between the precipitate and its ion. This is what we call heterogeneous equilibrium because see, this is solid and these two are aqueous. Applies to the reactions in which reactants and products phases. So I mean what we do not ever we are not going to be including solids into the K equation. So that thing here, is it possible to be here or not? The concentration of solids and pure liquids are not included in the expression for the equilibrium constant. So KSP is the solubility product constant. It's nothing. When we talk about the solubility product constant, we are actually talking about what? We are talking about equilibrium constant, but it's a different type of equilibrium constant where we are looking at the solubility product. What is solubility product? Solubility product is just dissociation of the solid into its ion or coming back. It's a reversible reaction. So KSP, like we used to call it Ka, Kb. Now it's not acid and base. It's about the solids going into their ions or ions coming into the solids. So we're going to represent that by KSP because this is not included. Solids and liquids are not included. The KSP expression is always going to be good. It's going to go like this. Okay, the ions only, the aqueous things will come into the equilibrium expression. We have discussed that earlier. So if you talk about the solubility product constant of KSP for several salts have already been calculated and tabulated. So consider the compound strontium chromate that you see here. Okay, that's a solid compound. It's a sparingly soluble compound, and we expect that very less because it's sparingly soluble, slightly soluble. We do not expect more of that, right? So that if we do not expect more of that, KSP should be towards minus numbers, right? It's very small. It's very small means the K is more towards this. Okay, less than one. If it's on that side, then it's plus 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 plus. We're gonna have a larger value of K then. That's this is what we have already discussed. You understand that part. So at equilibrium, the solution is saturated with dissolved ions. Okay, so at equilibrium, that's why we are interested in the concentration of the ions at the equilibrium because there we're gonna get the max it can come out of the solid. So when you look at the substance KSP at 25 degrees Celsius, because it's temperature sensitive, so at 25 degrees Celsius, they have reported different types of solubility constant for different compounds. So if you see the see how the numbers are going from -6 all the way to -32, this is very slightly soluble, which is aluminum hydroxide. So smaller the K value, KSP value, the less soluble that salt is going to be. So if you go by the examples here for the solubility equilibria, what is going to be the equilibrium expression? It's like that. Do not forget that whatever the mole ratio is, you're going to raise the power of the concentration to that. Okay, so if you see 2 here, it means you're going to raise the power to 2. If you see 2 here, you're going to raise the power to 2 here. If you see 2 here, raise the power to 2 here. If you see 3 mole ratio here, raise the power Do not forget that, but it's kind of a division. So writing equations and solubility products. So if we write the ionic equation for the dissolution and the solubility product expression for the following slightly soluble ionic compound. So they are talking about magnesium hydroxide, which is slightly soluble active ingredient in the milk of magnesia. So if you look at that solid, then if it goes into the dissociation, I expect that the KSP value should be a small number. But what is that number? That's what I'm trying to do. So what I need to do, I need to go like get the ICE for, oh, sending here. Sorry. So I need to go with the ICE again, right? ICE will help me figure out the concentration. If I go by I, C, and E, because I'm not going to use solid here, so I'm going to just cancel out this column. I'm going to work on this and that. Okay. So initially, what is the concentrations of this? And I'm going to move from there in my ICE chart, and I'm going to bring it to E. And then we're going to get that concentration. We're going to multiply that, and then we will get that, right? So interpreting the solubility expression in KSP. What does that mean? This is another equation here. You have solid, so it's going to be these two ions only in the K expression, and that equals to, that's going to be equal to this, right? So if you have a concentration of these two here, you will get this to this point here. Like all equilibrium constant, KSP has a fixed value at a given temperature because temperature affects equilibrium. That's the only thing that affects equilibrium, right? The product of the two ion concentration and equilibrium must have this value regardless of the direction from which equilibrium is approached. The direction is not a problem here, okay? The product of the two ion concentration at equilibrium must have this value regardless. So that is the value that's going to be the one for it. Okay, so if we talk about the calculation of the KSP from equilibrium concentration, if we are looking at the calcium fluoride and how it's going to dissolve or dilute, and because it's an insoluble compound, how do we know that? We're going to go by the solubility rules. We will understand that, okay, about the calcium and about the fluoride, what is the case in that scenario, and we will figure out sulfates of this calcium are exceptions in the insolubility. So where calcium is coming in with the halides, soluble compounds are halides, not fluoride in it. Okay, chlorine, bromine, and iodine in it, um, and and so on. So this is, and you can have your own solubility table, whatever is convenient for you. I do not mind that if you had one earlier. So if that is going to be the dissolution reaction, okay, here, here, and here. So it says the concentration of calcium ions in a saturated solution of calcium. So this is your question actually. Question starts from here. The concentration of calcium ions in a saturated solution of calcium fluoride is 2.15 times 10 to the power minus 4 molar. Okay, so then this is going to go like this. And if I go by I, C, and E, do I need to do that? No, I do not even need to go through the ice charts here, right? Why? Because the concentration of one of that is given already. So the concentration of calcium, and you know calcium fluoride, when calcium fluoride separates, how it's going to separate? If calcium, oh my God, sorry. Oh, okay, so calcium CaF2 here, right? So that's going to separate into 1 mole of calcium and 2 moles of Fa. 2 moles of F. So 1:2 is the ratio. So whatever the concentration you have for the calcium, twice of that is going to go for the fluoride. So that's 2.15 times 10 to the power minus 4. Twice of that is going to be for the fluoride. And what is that?
Isn't it in the problem, or am I misreading that?
What is in the problem?
Or, well, isn't it 4.3 times 10 to the negative
Yes,
4?
this
Oh,
is
okay.
given here. I'm just trying to confirm
Oh,
that
okay. Okay.
number on. Okay, so
4.3 times 10 to the negative 4.
Is this your answer? Okay. Twice of that times 2. Okay, so
Yes.
this is the concentration here. Okay, so now you have concentrations for both of them, 4.30. Even if it is not given, now you know how to calculate that, right? 10 to the power minus 4. Now you have to write down your KSP expression. KSP is going to be is equals to the concentration of calcium ions at equilibrium, and which is 2 plus. Do not forget that, right? That's wrong if I write this like this. This means it is a neutral atom. So 2 plus, and then times the concentration of your fluoride ions raised to the power 2. Plug the numbers in. You have to take the square of that, and 2.15 times 10 to the power minus 4 times 4.3 times 10 to the power minus 4 square. What is your answer for the KSP?
I had 3.96, or I'm sorry, 3.98 times 10 to the negative 11.
3.98 times 10 to
10
the
to the
power.
11.
Can someone confirm this number for me if this is the correct number here?
Yeah, that's what I got.
3.98 times 10 to the power minus 11. Okay, good. So KSP and the water solubility. So this is very simple. This the tricky thing is that you must understand if you have an ionic compound, when it's going to dissociate, it's going to give you 1 mole of calcium ions, it's going to give you 2 moles of fluoride ions. Once you know that, if the concentration of one of this, you can figure that out at your own because it's dissociating, and if it is not given to you, so you know that this is the concentration of the compound here, and if it is dissociate, it's going to dissociate like this, right? So 1 mole of this and 2 mole of this, so the twice of that is going to be the concentration of F. And do not forget to raise this power to 2 here, so that you're going to take the square of that by the formula that we have already discussed for the equilibrium expression so far. So KSP and water solubility, what does that mean? One way to establish a solubility equilibrium, what do? You're going to add a sparingly soluble solid to water and stir, right? So you're going to just add whatever amount you want to add, and you're going to quickly stir it with the help of a glass rod. Just keep stirring, and you're going to bring it to the maximum number of ions that can come out of that ionic compound. Eventually, the solution becomes saturated with the ions. In other words, the compound reaches its solubility. That's how much it is soluble. Can we increase the solubility? We'll discuss that later on. In a saturated solution, an equilibrium exists between the, so when it is all maximum number of ions, that's where it is actually acquiring its equilibrium. The reaction is acquiring the solution is acquiring its equilibrium. So we can calculate the solubility of a compound from its KSP. Okay, if the KSP is given to you, we can calculate the solubility value. The solubility will have units of moles per liter, which is molarity, and is called the molar solubility. Okay, so calculating KSP given solubility, and then calculating other things by going through. So when we talk about the common ion effect, so what we were discussing here is that we can calculate KSP given the solubility. So instead of calculating solubility from KSP, it is possible to calculate KSP of a compound from its solubility. So there are many sources listing the solubility of sparingly soluble compounds. Okay, that solubility constant that you were looking for. Depending on the source, the solubility values are expressed in many different units. So do not get confused with that. We must always make sure that the solubility is in molar solubility, means molar concentration. We need that, okay, when using the KSP expressions. That's the general rule. We need molarity. So if we talk about silver iodide has a solubility of 9.2 times to the power minus 9 moles per liter, what is going to be its KSP? What does that mean? First, write the expression of the KSP. This is going to be the KSP expression for silver iodide. We already know, right? Silver ions are going to be there and iodide ions is going to be there. Because when silver iodide dissolves, we form 1 mole of silver ions and 1 mole of iodide ion for each mole of silver iodide. If we know the solubility, we know the ion concentration, right? So if we know the solubility, it means it's about the ion concentration. That much can come out of that. And because it's 1:1, you're going to plug one number here and you're going to plug the second number here and then you're going to calculate the KSB the same way we were calculating it earlier. So it says determine the solubility product equilibrium constant for lead chromate. It is if its solubility is 4.3 times 10 to the power minus 5 grams per liter. So C unit here is in grams per liter. For the if we are calculating the equilibrium constant, we have to get into moles per liter, which is molarity. So pay attention to the unit because we are working on the KSP. So solubility of, so we're going to start with the solubility of the lead chromate in grams per liter. We can bring the solubility of the lead chromate into the moles per liter. Can we do that? Yes, if we need, if we can convert the mass into the moles, we can bring it into the molarity. Right, then you're going to have the concentration of the lead ions coming out and the concentration of this coming out at equilibrium, and that's you can calculate the Kp. So use molar mass to get to the moles per liter from the grams per liter. That's the first thing. Okay, so you're going to do that and you want to get your concentration in molarity. And we have been working on molarity since so many times. So now what do we need? We need a molar mass, right? We need a molar mass of what? Lead chromate, and that is the molar mass of the lead chromate that I've already provided here on the slide. Your molar mass can deviate a little bit, that's fine. But if it is like a significantly different number, then it's going to be a problem. So if you look at the lead chromate, that should turn out to be somewhere like this. Okay, so 4.3 times 10 to the power minus 5, you're going to convert that. So solubility is given to you, right, for this compound. So that it's grams per liter. We're going to bring it into the molar concentration, right? Once we are done, we're going to write down our equation like this, like we have been writing this equation there. And remember that this time this is going in this direction, but that's going to go get its equilibrium somehow, right? So lead chromate solid is dissoluting and probably coming back into this. So if the solubility of the ions is given to you, we know that this is again going to be 1:1 ratio here. So whatever the solubility given is going to be the solubility for both the ions. If you multiply both of them together, we're going to get the KSP value. It's very simple, nothing big in it, okay? This is the tricky part, which compound you are using, and if it's a 1:1 mole ratio or 1:2. If chromate was going to be 2, then you are supposed to multiply it by 2. That's all it is, times 2. So knowing the KSP of magnesium fluoride, which is this number here, we can calculate the solubility in moles per liter, right? So the same way we're going through the ice chart, we have to go through the ice chart. And here, what we do not know, we do not know the solubility at all for any of the ions. We're going to start with the ice chart as we have been doing here, and we have nothing to do with this here because it's solid, right? Solid never goes into the expression. So initially, we're going to say the concentration of both the ions is 0 and 0. As we move forward, change is going to be the x and 2x as per the stoichiometric ratio here. Then equilibrium concentrations are going to be d. So it means it's going to be 2x times x. But what I forgot is that 2x is going to be raised to 2 when we are writing the KSP here. It can be anything. It can come here, it can go there. It doesn't matter, right? You know, we are multiplying them. So it doesn't matter at all. So then you know that when you do this part here, so what are we doing there? Then we know the KSP, right? So we can write down the KSP here, 5.2 times 10 to the power minus 11, and that's equal to x times 2x squared, which is going to be equal to 5x, and then it's going to be 2.4. Is this the number correct? That if you guys are using your calculator, just let me know if the x is correct. So X is actually the solubility in moles per liter. And you know we're going into the moles per liter already. So example 6 is quite similar to what we have been doing so far. The KSP of calcium hydroxide, we're talking about calcium hydroxide, which is like soluble, sparingly soluble compound. And we can also look at this here. KSP is given to us. It's asking us to calculate the molar solubility of the calcium hydroxide. So the solubility product of calcium hydroxide is this. Okay, KSP is given to you, this. So do not get confused between the solubility versus KSP. Solubility is the concentration of ions that you see here. So what is asking you to calculate the molar solubility for calcium hydroxide. So what we're going to do, the reaction is this. We already know it's going to dissociate into this way. And you know that two OHs are going to come out of this compound, a mole of this compound. So do not forget this part here, that two OHs are coming out, because this is the trick here. Okay, only the critical part of the question or the solution is this small thing here. If you just lose that, if you do not know that you're supposed to write two H's here, then this is going to, it's going to take you to the wrong answer. First, write out the solubility product expression. You already know, because you know this 2 here is going to raise to the power 2 here. Now we can set up the ice table as we have been doing it so far, right? So it's initially 0 and 0, then x and 2x, then x and 2x here. So that's going to be the same way that we are doing it this way that we did earlier. That's how it's going to go. Okay, so that's going to be 4x cubed. So you're going to take the um, cubic root here, okay, of the numbers. You're gonna do 4 is gonna go down here. You're gonna take the cubic root for that, and then you will get the value of x. That turns out to be this. Therefore, the molar solubility of this is going to be that. So KSV, because it's just the repetition of the same stuff that we have been doing so far. So, and because we are dealing with very small numbers, so it's potentially it is, the change is already insignificant here, that you already know, because it's a sparingly soluble salt. So we're going to just be playing with what we have, and that tells us the solubility, molar solubility of the compound. So KSV and the common ion effect. Yes, you remember the common ion effect? That common ion effect will take its part in the KSP, because if I have sulfate ions as a common ion effect, what will happen? That's gonna that's gonna cause the system to go back to this side, right? Then we have like even the solubility product is gonna go even a smaller number for this system, right? You know that, right? Because it's coming on more and more. Whatever is going to dissolute into, it's not going to go into that concentration, because it's going to push it back to this side. So how would you expect the solubility of barium sulfate in pure water to compare to its solubility in 0.10 molar sodium sulfate, right? So solubility in 0.1 molar sodium sulfate must be less than in its pure water. That's what we get from the, this is the common ion here. That's what we get from the Le Chatelier's principle, right? So go review that. It's again a recall thing in this chapter. So if we look at the example 7, calculate the molar solubility of cadmium sulfide in a 0.01 molar solution of cadmium bromide. The KSP of cadmium sulfide is this. Wow, oh my God, what is going on? Bromide, and sulfide. Calculate the molar solubility of calcium sulfide. This is our compound in a solution of 0.010 molar. So cadmium bromide is also there. So the common ion is going to be the cadmium. This is already cadmium bromide solution where you are adding your solid cadmium sulfate. So that's the solution. Okay, here in that you are adding this, and then you are trying to look for that how soluble it is going to be. Definitely there's going to be an effect of the common ion, because cadmium is there, right? So the initial concentration of cadmium is not going to be zero. It's going to be this, because this is the common ion, right? So if we go by so you have to go by the same stuff, the ice chart. But what is tricky here? We have to figure that out, that this is and that's in exam. It's not going to tell you that it's a common ion effect. It's a problem related to the common ion. You have to read and figure that out at your own. Okay, is this a common ion effect one thingy, or is it just a simple thingy like we were doing it earlier in the chapter? It's not as simple. It's with the common ion effect. So when you're reading it, pay attention that it's a common effect, the common ion is there or not. Because what my experience is from the students is that they just mess up on this point. They do not know what I'm asking for. They do not know what the question is asking for. They're lost because they are not able to pick to read it and pick it up. Okay, they're asking you few things in the question that helps you understand what is going on. Is that it says calculate the molar solubility of cadmium sulfide. The first thing that that should come into your mind is asking about an ionic compound. Okay, cadmium sulfide. It's not asking about acid. It's not asking about base. So it's more toward KSP problem. This is how I will go to that. Then in a zero point 0.1 molar solution of cadmium bromide, so this is what I try try to do to explain that this is what it is saying. The question is saying that this is in this solution, cadmium bromide solution already. And cadmium bromide, I know, is a soluble solution. So where there I'm going to have cadmium ions and I have bromine ions as well. So now I know from the solubility rules also I know that this is going to be there. And if I add cadmium sulfide here, which is a solid cadmium sulfide here, and then now I'm looking for how much it is going to dilute, definitely the cadmium is going to play its role in pushing it back towards the solid. So I started with the initial concentration given for the solution here. So the sulfides are going to be zero at this point, and the change is going to be x and x, and then this is going to give it a different scenario, right? So 0.010 plus x, how much is going to be there additional to what is already there? And then we need to figure out that additional value of x, additional amount of cadmium here, x, right? So 0 plus x is equals to x, how many sulfides are going to be there. So this is our expression because it's 1:1 ratio in cadmium sulfide. So the KSP value is so small compared with the cadmium concentration, we can assume that the change between the initial concentration and the equilibrium concentration is negligible. So if we just say that this change is negligible, then what we are doing, they are not coming out. This remains more so the concentration that was there for the common ion from the solution, it's nearly close to that, right? We do not even need to calculate that. We just need to figure that out from this part here. And because it's talking about this KSP value, this large, huge KSP value, right? So so you can do that if you want to. Let's say if you just ignore this change here, then this is x is not going to be anything. So what it means that it's going to be the KSP here is equals to 0.010. What is the value of KSP? Oh, what I'm doing wrong here? Am I doing wrong? Something wrong? Since the KSP value is so small, this value here, compare with the cadmium concentration. Okay, this is the cadmium concentration. This is too small. We can assume that the change between the initial concentration and the equilibrium concentration for what? For cadmium, it's negligible. So we're going to say, okay, the solubility product or the molar solubility, not solubility product, sorry, solubility product is this. The molar solubility of the cadmium sulfide, it's like this. It cannot go more than that because that's the initial concentration. So it remains like this, whatever, wherever it is. So solubility and precipitates. Recall from chapter 13, equilibrium can be approached from either direction. You can do something here, you can do something here, or whatever things are disturbed on any of these ends, then it's going to go towards the equilibrium again. Starting with just reactants, add solid compound to the water. You're going to have more and more of this, and then it's going to achieve its equilibrium. Starting with just products, add ions to water. You're going to have more and more solid. So if you want solid to appear, just add ions. And you know we have been doing it so many times in general chemistry one when we were mixing solutions, we are actually giving these species to just form some precipitates. KSP and precipitate formation. KSP values can be used to predict whether the precipitate will form from when ions are going to be added, right? So if it KSP value is too small, it's very difficult for it to form ions, not precipitate. If KSP value is too large, it's not that small. That means it's going to go more into the ions. So Q is of the same stuff. So this is the exact same analogy that we have been using so far. So at any point, if we are looking at the numbers, that's going to be the quotient here, Q, and at equilibrium is going to be the K value for the solubility products. It's exactly the same thing. So the relative magnitude of Q versus KSP will indicate whether a precipitate will form or not. We already know that part, right? So if Q is greater than KSP, a precipitate will form, right? A precipitate will form because you have more ions. So ions needs to go into the to the solid side. If Q is less than KSP, the solution is unsaturated. No precipitate will form, and if desired, more compound can be dissolved. Okay, and if Q is equal to 8, that means it's in the equilibrium point of precipitation, just at the point of precipitation. So blood will not clot. This is an example of that. That blood will not clot if calcium ions are removed from its plasma. Some blood collection tubes contain salts of the oxalate ions. Okay, this is about when you are taking the blood out of your arteries, and you're gonna keep it right the same way it is in your artery. So what say blood will not clot. We do not want blood to be clotted. So the tubes that we use to collect blood sample already have it carries calcium ions in it. Okay, so blood will not clot if there is something in it that removes the calcium ions from it. Blood will not clot if calcium ions are removed from its plasma. Some blood collection tubes contain salts of the oxalate, so calcium oxalate can be formed. You know the calcium oxalate that precipitate in our kidneys, right? The kidney stones, calcium oxalate. So ions, so the calcium oxalate ions. If you have calcium in the blood, and if you can just take it out from the blood, okay, then you can keep the blood in unclotted form. Okay, so calcium needs to be removed from the plasma right away once you take it out from the artery, from the body. And how you can do that? You can make the salts of the calcium with oxalate. Okay, so oxalate is added into the tubes, and the calcium is going to go with that. And calcium, so at sufficiently high concentration, the calcium and oxalate ions are forming salts that is going to be this, which also contain water bound in the solid form. Okay, so this is the calcium oxalate salt having water molecules attached to itself. The concentration of calcium in a sample of blood serum is 2.2 times 10 to the power minus 3 molar. Concentration. What concentration of oxalate ion must be established before you can form this compound? Okay, and before you want it to precipitate. So it means what concentration of oxalate ions should be there to precipitate the calcium out of the blood sample. Okay, that's what the rationale is. So the equation is going to be like this. We are from calcium oxalate, which is a solid. You're going to have calcium ions coming out of that. It's 1:1 thing. So for the reaction, Q is equal to KSP is equals to this is here and that is here. So that is equals to 10 to the power minus 10 to the power 10 to the power minus 8. So you will say, where is this coming from? That should be given to you for the KSP. Okay, so then 1.96 times minus 8, the KSP is already given to you. This is the KSP given to you. Then you have the concentration of what? Concentration of calcium ions that you are supposed to chill. That is called the chelation of the ion. Okay, so what you're supposed to take out, then you can just figure out what the concentration of the oxalate ions would be. That gonna go completely with this to just get this number here, and that is where it will start precipitating. Okay, so you just figure that out. It's simple. It's a very simple math here. Okay, it's nothing big in it. So concentration of this much of the oxalate ions is necessary to initiate the precipitation of the calcium oxalate under these conditions. And that's why it's important. Sometimes that's what I have said earlier. Sometimes we want precipitates to be formed. Sometimes we want precipitate to dissolve. This is what we do in chemistry. We can even significantly increase the precipitations. There are ways to do that. Okay, consider a solution of two kinds. So what is this called? Selective precipitation. If you have a mixture of things, which one is going to precipitate first? That's sort of question. It's like a puzzle thing. Consider a solution of two cations. Let's say there are two cations present in a solution. One way to separate the cation is to add an anion that will form precipitate with only one of them, right? So if you have Cl negative here, and if you have Cl negative here, not here, just clear that. If you have oh, if you have Ca, let's say one cation, 2 plus, and you have Na plus, right? So now you're gonna add anion. If I add S2 plus, which one is going to be precipitate out with the sulfide? My sulfide is gonna take out this. That's gonna make a precipitate. Sodium and sodium sulfide is soluble. Okay. The precipitate can then be removed by filtration. There are physical means to do that. It's like a sieve. You have a sieve of filter paper is a sieve, very small pore size. You can just pour your pour your precipitate on top of that. The liquid is going to go down, and this is how you can separate your precipitates. Okay, and the other cation will remain in the filtrate, so that is passed through the membrane. This is retained in the membrane, so you because it's converted into the solid now, and this is remains soluble in the water part, so that's going to filter out. Okay, so the it's going to go into the filtrate part, which is the part going down into the funnel. Okay, from the funnel. So this approach is called selective precipitation, and is often used as a method of purification in the labs. So selective precipitation, what is selective precipitation? Example solution of magnesium and sodium ions. I've already given you an example, but you can discuss it here as well with the carbonate. Okay, ions are slowly added. Most sodium compounds are soluble in water. That's why I gave you the example of this. Okay, magnesium can form a compound with carbonate, which is only sparingly soluble. And if you go by the solubility rule, we will also, if we have memorized our solubility rules and if we know the solubility rules and we know that the carbonate salts are insoluble. Okay, so pretty much down to what we were supposed to look at. So now consider a solution of magnesium and barium ions at the same concentration. Okay, so barium adds a low. So now I have cations. Okay, they both can be precipitated. Like I have barium and I have magnesium here. Just a minute. Ruba? चावल उबाल लो चावल उबाल लो उबाल लो रात के लिए okay okay so you hear me now. Okay, so we're talking about two ions. They both can go with the carbonates. They can precipitate with the carbonate. But if we look at the Ksp value, which one is going to precipitate first? Definitely, this one is low solubility product, so this probably is going to precipitate first. The difference in solubility can still be used to separate the cations if carbonate ions are added very carefully. Which carbonate complex will precipitate first, the least Ksp or the highest Ksp? Definitely this one, right? Or this one. This has more tendency to go towards the solid. We cannot always, but this strategy that we are looking at, and we are trying to compare two Ksp values for both the compound, and then we are trying to predict, okay, if we're going to mix them, which one is going to precipitate first and which one is going to precipitate later. And so if we just control the concentration of the carbonate ion that we are adding, we can actually selectively precipitate by comparing the Ksp. That's not the case always. Okay, we cannot always compare Ksp values to answer this question. Why? Only two conditions must met if we are using the KSP. If one of this is not meeting, both of them should met. must meet. Okay, if these are not meeting, we cannot compare the KSP values. When can KSP values alone be used to predict which compound will precipitate first? Here, both ions to be separated must be the same initial concentration. If you are using two ions, cations, to be separated with the selective precipitation method, then this initial concentration for both of them should be same. If the initial concentration for two ions like we are using here are not same, we cannot compare the KSP values. The second condition is that both complexes must have the same cation anion ratio. Okay, so if you look at it here, it's 1:1, 1:1. Both of them have this tendency to have 1:1, 1:1 mole ratio with carbonate ions here. So if so both conditions that we are talking about here are one meeting here. That's why we were comparing the KS. If any of this condition is not met, we cannot compare the KSP. There is another way of doing that then. Both of these criteria must be met. If not, then calculations must be done to determine which compound will precipitate first. And here's an example of that. Okay, so a solution contains 0.0010 mole of Ki, okay, and a 0.10 mole of KCl. So uh, what condition is not meeting from here is this one, because they both are 1:1 ratio. The both of these compounds are 1:1 ratio. But what is not, so ratio remains the same, right? That's this is asking you for. What is not meeting is the concentration. This is 0.0010 mole concentration, and this is 0.10 mole concentration. That's why we cannot compare the two KSP values for Ki and KCl to predict the KSP of the which one is going to precipitate first for the selective precipitation. So then we're going to look at these two reactions of the dissociation or dissolution of these compounds, right? What we are adding, AgNO3 is gradually added. It means we are introducing silver ions into it. Okay, so it means this is going to be added gradually. Add to the solution, which forms first, solid silver iodide or solid silver chloride, which will form first. So if we're going to look at the KSP value for both of them, this is less, AGI is less, and this is a larger number, right? It's a big number, but we cannot compare. We have to go through and figure that out what's going on. If the solution contains about equal concentration of chloride and iodide, then um, the silver salt with the smallest KSP would precipitate first. Okay, but here iodine and chlorine, they are different concentrations. The concentrations are not equal. Okay, these are not equal concentrations. However, so we should find the silver concentration at which silver chloride begins to precipitate and the concentration of silver at which the silver iodide begins to precipitate. Okay, the salt that forms at lower concentration of silver is going to precipitate first. So this is the key in handling all the problems. This is the key. So just look at that and go through it. So for silver iodide, what we're talking about, silver iodide precipitates when Q equals KSP for silver iodide. Okay, so what are we looking for? This is for the silver iodide given to us here. So we're gonna we have the KSP in hand, and the concentration of I is this. Where is this we getting from? We're getting this from here. This is from here. So now if we write down the Q is equals to the concentration of both of them, then silver is here and the concentration is here, the KSP here. So we can find out the concentration of silver required to start precipitate of that compound. Okay, so this is going to be 1.5 times 10 to the power minus 13 molar concentration of silver ions. So A silver iodide begins to precipitate when silver is this molar concentration. For AgCl now, it still precipitates when Q equals to Q. So this is the concentration for that. Okay, when so this is the KSP value. Where are we getting this from? This is given to us already here. Okay, so then we're going to put that into the expression. Okay, this is the expression. You're going to put that in. You're going to find out the concentration of silver ions, and that turned out to be this. So what is more and what is less? The concentration. This requires less concentration of silver ions to start precipitating compared to this one. The salt that forms at lower silver concentration precipitates first. So in order for that, what we figured out that this AgCl begins to precipitate when this concentration is this, then silver iodide begins to precipitate at a lower silver concentration than AgCl. So AgI begins to precipitate first. As simple as that. The second topic that we were going to look at is the Lewis acids and the bases. So Bronsted-Lowry, we already know what is Lewis acid, accepts a pair of electrons. Okay. What is Lewis base? That donates a pair of electrons. We're talking in terms of the acceptance and the donation of the pair of electrons. A Lewis acid base reaction produces a product with a coordinate covalent bond. This is the most important thing. When Lewis acid base reaction is happening, a coordinate covalent bond will form. What is coordinate? What is a coordinate covalent bond? We'll discuss. It's a different type of bond. How do we define that? It's here. A type of bond that forms when one of the atoms in the bond provides both bonding elements. Okay, that's going to be the central one. Okay, both bonding electrons. So that is going to provide the both. So keep that here, your concentration on this definition. A type of bond, what is a coordinate covalent bond or a coordinate complex bond? A coordinate covalent bond is a coordinate complex compound, is a type of bond that forms when one of the atoms in the bond provides both bonding electrons. Means the, the first bond which is going to be formed. We have always discussed that if we have X atom here and if we have Y atom here, then one electron is from here and one electron is from here. The first bond is always going to be formed by this, right? Formed like this. Then if the second bond is going to be introduced, then a lone pair can go and can be there as a double bond. No, in the coordinated covalent bond, the first bond is the donation of both electrons from one partner. So if we talk about X and Y here, then Y had nothing, but X had both the electrons for the first bond, even for the first bond, and it shared between the two. And this is how the first bond was established. And that's what we are called coordinated covalent bond. Coordinate covalent bond. A coordinate covalent bond occurs when a water molecule combines with a hydrogen ion to form a hydrogen. So in hydronium ion, it is actually a coordinate covalent bond which is going to be formed. Lewis base electron pair donor. What is that electron pair donor? We have already discussed electron pair acceptor is an acid. Pair acceptor is an acid here. Pair donor is a base here. So do not forget that. Okay. The definition is acid accepts a pair, base donates a pair. Pair of electron. That's different than Lewis acid and Bronsted acid and bases. The concept of donation and donor and acceptor. Okay. So if you talk about the Lewis base adduct, what is Lewis acid base adduct? A compound that contains a coordinate covalent bond formed between the Lewis acid and base. So when you mix a Lewis acid with a Lewis base, then the compound is formed, and then compound is going to have a coordinate covalent bond in it. When the compound is going to have a coordinate covalent bond in it, we're going to call it an acid base adduct. As simple as that. So what is going on? If you look at these Lewis forms of both of them, then BF3 is, this is an example of an electron deficient compound. It exists like this. So do not tell me that this is the wrong structure. I mean, that's your knowledge that you already know about the BF3. It's an electron deficient Lewis structure. So when it comes with the fluorine here, then there are no lone pair of, there's no lone electron on boron that needs to be shared, right? So there is nothing on the boron. If then there is nothing on the boron, and this is taking so long to be wiped off. I want to remove this. right? So this lone pair is going to be introduced between these two to give you the first bond between the two, which is this coordinate complex bond. Okay, so if you look at the ammonia and you look at the silver, silver has nothing on it, but ammonia has a pair of electrons. Ammonia is just gonna use this pair of electron between the two, and how in the fashion of two ammonia molecules are coming with just one silver ion here. Okay, so this is two ammonia molecules. So this is going to be attached here. This is going to be attached here. Okay, so this bond is with the first molecule's lone pair. This bond with the second molecule's lone pair, and that's what we know, right? That's what we have been saying so far about the coordinate complex, coordinate covalent bond. Okay, so displacement reaction, what is displacement reaction? Many Lewis acid-base reactions are displacement reactions. Either one Lewis base displaces another Lewis base. Okay, so we had this acid-base adduct formed by the Lewis acid and the Lewis base reaction. If we add another base in it, and that base has a tendency to replace the existing base here, that can happen. Okay, and that's just called displacement reaction. Either one Lewis base displaces another Lewis base. Many Lewis acid-base reactions are displacement reaction. Okay, so another base comes in and it replaces the other base. So there's another form of new adduct is formed. Okay, so a familiar displacement reaction is hydronium ion. Okay, so if you look at the hydronium ion, this is your water molecule. This is your HCl molecule. So hydronium is going to be found when hydrogen is going to come out of this and it's going to be is going to go into this, and which this lone pair is going to be used to have a bond between this oxygen and hydrogen. Yeah, this bond. Okay, see the chlorine is with its lone pair. It's never it is never given to anything. So that's hydronium ion is a new adduct with the acid-base reaction. Oh, sorry, acid in the water. This is an example of the Bronsted-Lowry model overlapping the Lewis model. So certain acids which are Bronsted-Lowry acid are also the Lewis acids as well, but that's not true for all of them. The second part, the next part here is to discuss the complex ion. And complex ions are actually the compound that have the coordinate covalent bond in them. Okay, many Lewis acid-based addicts are complex ions. Complex does not mean it's bad always. It's we'll see what are the applications of the complex ion. So complex ions are polyatomic ions. They see this charge here in parentheses. This style of writing or drawing Lewis structure tells us that this is a polyatomic ion that consists of central atom. So there is usually a central atom in these complex ions, usually a transition metal. It can be silver, it can be zinc, it can be iron, surrounded by ions. So these one ion and this second ion, or a molecule called ligands, or you can call it ligands as well if you want to. Okay. So these are the ligands. This is the central atom. These are the ligands. This is having the molecule is having an overall charge. It's a molecular compound, so it's actually a polyatomic ion. These are ligands are Lewis bases. These ligands on both sides are Lewis bases. The charge of the complex ions equals to the sum of the charges of the ligands in the central atom. So silver is plus one plus. Okay. So this formula of a complex ion cannot be predicted. Like you see it here, this is not a predicted structure by the Lewis structure. That has actually been experimentally determined. And that's how we know they are very complex. Instrumentation is not capable of figuring out their structure. Sorry, prediction is not capable enough to have you write down or draw a Lewis structure or three-dimensional structure of the complex ions. They only experimentally determined. The central atom ligand bonds are coordinate covalent bonds. So this bond and this bond are coordinated covalent bonds. Complex ions are sometimes called as coordination complexes as well. Okay, coordinate. What is the application of coordination complex in chemistry? It's a very good example that we're going to discuss later on. Complex ion equilibria. Okay, so when we're talking about the complex ion, definitely complex ion equilibria can also be a thing, right? it can dissociate, or it can dissolute, it can form. Okay, this is if this is forming, if the complex ion is forming, we're going to call it the formation constant. The equilibrium constant that we are calculating for the formation of the complex ion is going to be called as formation constant. So you have another terminology about the equilibrium constant. We had KSP, then we have KF. So remember that KF is always for the formation of the complex ion, equilibrium constant in the formation of the complex ion. So whatever the ions were, see a metal, a transition metal is here, and then two bases are here, Lewis bases. So the quadratic complex that's going to be formed is here. It is your complex ion. We can also call it the coordination complex. Formation constant, equilibrium constant for the formation of a complex ion directly from its component. These KF values are generally very, very large. That means that it's very difficult to dilute complex ions. This reaction is very feasible when you put these ions together. They love each other. They're going to go into the complex ion, okay? And that's why they would really would like to come back into their ionic forms. And that's why the KF values are very, very large. Dissociation constant, when we're talking about the dissolution of the complex ion, then you will say when if the kf is high, it's very, very large, then kd is definitely going to be a small number. Means dissolution or dissociation is not that feasible. The inverse of the formation constant is the kd, and kd is the equilibrium constant for the decomposition of a complex ion into its components in a solution. Can we, so if the kd for the complex ions is very, 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 very small, means if it's very large here, then can we increase the dissociation? Can we increase, or can we somehow enhance more dissociation if we need it? We will see those ways as well. Okay, so formation constant, what is formation constant? Is the formation of the complex ion. Look at the numbers: +7 plus 19, huge numbers. That tells us that the complex ions or the coordination complex are very stable compounds. So when we talk about the multiple equilibria, sometimes more than one equilibrium is needed to describe a process. Okay, uh, so how dissolving an ionic solid with a strong acid, there are multiple things going on. Dissolving a sparingly soluble solid by complex formation. Okay, so what we can do, we can dissolve an ionic solid which is sparingly soluble by adding a strong acid into it. So we can add a strong acid and we can have more and more ionic solid to be dissolved. Okay. Then in the second way, what we can do, we can dissolve a sparingly soluble solid by complex ion formation. We'll see how we can do that. If it's an ionic compound which is less soluble, we can increase its solubility. You can have it more go into its respective ions or become soluble from the solid by the help of the complex ion formation. The carbonate chemistry in our ocean revolves around the multiple equilibria where dissolution of things happening based on other stuff. Dissolving precipitates means two methods of dissolving compounds that are sparingly soluble. Add a strong acid or add a ligand, Lewis base, that can react with the metal cation of the acid and form the complex ion. That's exactly what we have been discussing here. So dissolving precipitate. So what is the phenomena? There is nothing much in it. Just look at it, what's going on. As we all know, a strong acid produces hydronium ion when in water. If hydronium ion can react with the anion of the complex, then strong acid can be used to dissolve compounds that would otherwise have very low water solubility. Do you understand that part? That's what is going on. Okay, so if you have if this the hydronium ion which is going to be formed when you add a strong acid into the water, if and that can react with an anion, with the anion. Okay, any anion present there. Okay, and then a complex that is going to be there, and then strong acid can be used to dissolve compounds that will go move forward. The following types, and we'll discuss that. Okay, here in with the example. The following types of compounds tend to have increased water solubility in the presence of a strong acid. So if all complexes that contain hydroxide, means all compounds, all acid, all ionic compounds that have that have hydroxide in it, if you add HCl in it, definitely this OH will come towards, will go and react with this, so it's going to dissolute. Okay, more and more ionic salt will dissolute because there's a tendency for OH to go with the H here. Many complexes that contain NH3 or an anion that is a weak base can also go for more solubility when you add a strong acid into it. Dissolving hydroxide containing compounds with a strong acid, as we have been discussing it here, right? So let's see with example, if you have zinc hydroxide, which is this is the formula, that's solid, that's insoluble, or sparingly soluble salt that does not solubilize well. It's just a very insignificant solubility where the zinc is going to be separated from hydroxide. So if we add a strong acid in it, can we just separate these two from each other? More of them come out into the solution, come out from each other, and means solubility is enhancing. This reaction takes place as two equilibria. What is going on? First, that is going on into the zinc and then to H. Whatever. So it's let's say it is the dissolution or the dissociation of the solid into the ions is very less. Whatever it is, some of that is going to come out, right? If we can react this with the added acid, it is again we are going to go with the Le Chatelier's principle. We are removing this. So once you remove any of the product from the product side, then the reaction's direction is going to go to achieve the equilibrium, right? So it's going to go from left hand side to the right hand side because more and more of this needs to be present or need to come out, right? To achieve the equilibrium. And that's how we are pushing the solid to go more in. What we are doing, we are just utilizing one of the products here with the acids proton here, and then we are actually disturbing the equilibrium. And when the equilibrium is disturbed in a way where we are removing one of the products, then more of the reactant is going to go into the product. And that's how we are increasing the solubility of this sparingly soluble compound. So dissolving hydroxide containing compounds with a strong acid, we have already covered that part. Okay. So you know what I was trying to say. You can read it if you want to. I've just said that, all of that. So complex, so the second way of doing is with the complex ion formation. We can also do that. There are two ways, adding a strong acid or making a complex ion. Some Lewis bases can dissolve ionic compounds if they contain metal cations that form complex ions with these species. So we had this here, right? We had zinc hydroxide. So the zinc is going to come out of that. We already know that. Zinc 2 plus. It just goes with only one ionic state, which is 2 plus. So if I can add two ammonia molecules into it, which are the Lewis bases, right? See here, then I can actually make a coordination complex. The same phenomena is still going on in here as well. What I am doing, I'm just removing one of the products from here. By doing what? By adding the Lewis base into the solution. Lewis base is going to form a coordination complex, and you know the Kf for the coordination complex is so high. So when this is formed, this is a very strong product. It's going to stay there. It's going to stay there. So more and more zinc is going to be reacting with this ammonia molecule, and this is how more and more zinc hydroxide is going to be dissociated into the respective ions. Okay, and that's all about the chapter number 15. You have learned two ways of how to dissolve sparingly soluble compounds by the help of the strong acid and by the help of making the coordination complex.